So Curie was focused on discovering different radioactive elements. Ernest Rutherford and other scientists were interested in characterizing the radioactivity. Okay, we've got these radioactive elements, but what is this thing, this radioactivity? So the nuclei of radioactive elements are unstable, and they will spontaneously decompose, just fall apart, emitting small pieces of themselves, and in doing so, they become more stable. There are 4 types of radioactive emission: alpha particle, and that's symbolized with the Greek letter alpha. So alpha rays, beta rays, that's the Greek letter beta, gamma rays, that's the Greek gamma, and positrons. So 4 different types of radiation. So we need to review nuclear symbols. We learned this before when we talked about isotopes and different numbers of neutrons. So the nuclear symbol here, we've got the chemical symbol for the element, and on the left as a subscript, the atomic number symbolized by Z is the number of protons, and the mass number is above that, symbolized by the letter A. That's the number of neutrons plus protons in the nucleus. So mass number, sum of protons and neutrons; atomic number, number of protons. To find the number of neutrons, you subtract. And this is stacked up like you were going to subtract, and so you take A minus Z, and that gives you the number of neutrons. So hopefully you remember some of that. Most elements have several different isotopes. Some have 2, some have 3. You can't predict from the periodic table. When we talk about a particular isotope of an element, it's often referred to as a nuclide. So that's a particular isotope. We can characterize the isotopes by the element name or its symbol followed by the mass number. So we can talk about carbon-14. We can call it carbon-14 or C14. So that's the element symbol followed by the mass number. So for carbon-14, we can also write that as carbon-14. That's the mass number. What's the atomic number for carbon? 6. It's element number 6 in the periodic table. So how many neutrons does carbon-14 have? 14 minus 6. 8. Yeah, right? Isn't that nice? See, this is protons plus neutrons. This is just protons, and you subtract them and you get the neutrons. So the 3 main subatomic particles, and we've talked about these, protons, neutrons, and electrons. We can also represent these with nuclear symbols. So the proton, instead of an element symbol that's capitalized, we use a lowercase p for proton. How many protons does a proton have? 1. And how many neutrons does a proton have? It doesn't have any neutrons, so its mass number is 1, because it's a proton, right, with no neutrons. And here we have a neutron, symbol N, lowercase n for neutron. It has 0 protons. Its mass number is 0 protons plus 1 neutron. It's a neutron. And then there's the electron. The symbol for the electron is a lowercase e. Its mass is essentially 0. It doesn't have any protons or neutrons. This is the part that will be explained later. The atomic number is -1, which suggests -1 protons, but that'll clear up later.
When would we use that, or why?
Oh, we'll get to it right now. So in alpha decay, what happens is an unstable nucleus emits a particle composed of 2 protons and 2 neutrons. And this is the alpha particle. So 2 protons and 2 neutrons, the atomic number would be 2, because 2 protons. You add those together, the mass number is 4. This is the same as a helium nucleus. And so we give it the same symbol as you would give to helium-4. But it's not a helium atom, it's just the nucleus. So it's identical to a helium nucleus. So this picture is a large nucleus. We're not showing electrons. Here's the nucleus, and part of it shoots out two neutrons and two protons together, and that's the same as a helium nucleus. It's called alpha decay. You do need to memorize that an alpha particle is this, right there. You should know that. So, a reaction is occurring. Things are changing, and so we represent these processes with nuclear equations. So in this example, here we have the parent nuclide. So uranium-238 will spit out a helium nucleus, an alpha particle. So it loses two neutrons and two protons, and it forms thorium-234. In these nuclear equations, the mass numbers on one side have to equal the sum of the mass numbers on the other side. Because this would be the number of protons, right? We started out with 92 protons, and this is like coming apart, separating into other things, but we still have 92 protons. So 90 plus 2 equals 92. Here's the mass number. We can't have protons or neutrons really just, I shouldn't say that. The mass numbers also have to be equal. So 234 plus 4 is 238, and that's what it is over here. So the superscripts must add up to the same total on each side of the arrow. And the subscripts have to add up to the same total on each side of the arrow. So in nuclear reactions, elements often change their identity. That doesn't happen in chemical reactions. In chemical reactions, if you start with an atom of uranium, you do the reaction, maybe it combines with things, but it's still uranium. This is the exception that we refer to occasionally, except in a nuclear process. Here an element can change into another element. It's nuclear chemistry. We can figure out what that daughter nuclide is. This is the parent, and after this reaction, this is the daughter, because the parent, you could say, gives birth to the daughter. I don't know why they're feminine, but they are. We can figure out what that daughter nuclide is by balancing the equation, the superscripts and the subscripts. So if we have thorium-232, and we know that it emits an alpha particle, there's going to be something here plus an alpha particle. So what we need to figure out is x plus 4 is going to equal 232. So x plus 4 has to equal the total on that side. So x plus 4 equals 232. X must be 228. The lower number, the atomic number, is 90, and here y plus 2 has to equal 90. So y is 88. Any questions? Yeah, what element is that? Well, you're going to look at this atomic number down here. So 88 is radium, Ra. So this would be radium. And down here, the atomic number is 88, and the mass number is 228.
So does this have people like find new elements and stuff that are like missing?
No, this is not how we find new elements. We'll get to that, though. It's in the chapter. So write the nuclear equation for the alpha decay of PO216. Well, we start with the nuclear symbol for PO216. PO is polonium, but you don't have to know that. 216 is the mass number, so that goes on the top, on the left. And PO is PO behind the globe. 84? Element number 84. There's a globe strategically blocking the lower right corner of the periodic table. Alpha decay. So that means that it emits an alpha particle. Normally the alpha particle is written second in the equation. It's not that important, but I'm just going to follow that pattern. We need to know the symbol for an alpha particle. It's that helium nucleus. And then we're filling in this gap here, the nuclear symbol for the daughter nuclide.
82.
Yeah, so 84 is the total for the mass number. Here we have 2, and so the mass number of this new one makes up the difference there, and so it must be 82. So the mass number is 82. 82 plus 2 equals 84.
How did you get the helium there? Or why is it?
This is an alpha particle. You memorize it.
Oh, so for every line you have to use that one?
If it's alpha decay, then it's this. Yeah, so that's the alpha particle. Well, then we can find 82 on the periodic table. Lead? Thank you. It's also behind the globe. I'm going to have to move the Earth. Yeah. It's lead. Okay? Then we need the mass number for this. So 212. Because 212 plus 4 will equal 216. So we've got 216 on the left. That equals 212 plus 4. And 84 on the left equals 82 plus 2. We're just looking at adding, subtracting with whole numbers. You can use your calculator. It's absolutely fine. So there's the nuclear equation. Any questions? We need to have just a general understanding of the characteristics of these different types of radiation. So we use an analogy with different sorts of vehicles. We've got 18-wheeler trucks and 4-door sedans and motorcycles. So alpha radiation is like the 18-wheeler truck. It's this big semi-truck, right? It's massive. It's the biggest of the particles that are emitted. So it has the highest ionizing power. Ionizing power is the ability of radiation to ionize other molecules or atoms, to knock electrons off. So if you think about driving this into a brick wall, is a semi-truck going to do a lot of damage to a brick wall? Yeah, it's going to smash it up, right? So that's ionizing power. It has the lowest penetrating power, though. So the analogy for penetrating power is you've got a bad traffic jam. How do semi-trucks do in traffic jams? Not well. They're just pretty much stuck. They just have to go along because they cannot change lanes quickly. So they're just kind of stuck there. They can't penetrate through the traffic jam. So we've got the 18-wheeler truck. Ionizing power is smashing a brick wall. And penetrating power is getting through a traffic jam. Ionizing power is significant because that's what causes the damage to living organisms. Your body has all these complicated chemical reactions occurring in it, and when you ionize some of the molecules and atoms in there, then you mess up all those reactions and cause lots of problems. The cells may die, they may reproduce abnormally, causing cancer, or all kinds of crazy things. Penetrating power is the ability of radiation to penetrate matter, to go through solid matter. In order for radiation to damage your cells, it has to get into them, right? Alpha trucks, Alpha particles have low penetrating power because of their large size. So you think of a semi-truck in a traffic jam. Alpha particles can be stopped by a piece of paper, by a t-shirt, even by a layer of air. So they cannot get through very well. So they're relatively safe outside the body, but they're really dangerous if you inhale them, get them into your lungs, or swallow them. Because once they get inside of you, they can cause a lot of damage. The next one is beta decay. In beta decay, an unstable nucleus emits an electron. Now, what seems wrong about that? Are there electrons in the nucleus? No, there aren't. So how does this work? Well, this is the symbol for a beta particle. That's the symbol for an electron. What's happening here is that a neutron can turn into a proton and an electron that gets spit out. Proton has a positive charge, an electron has a negative charge, so the charge thing works out. So we can say that a neutron can come apart into a proton and an electron. And that's why the symbol for the electron is -1, because this -1 and that 1 add up to the 0 for the neutron. And the superscripts work out as well. So we can have radium-228 undergoing beta decay, spits out a beta particle, and then we can figure out what the daughter nuclide is the same way we've done before. 89 and -1 add up to 88. 228 and 0 equals 228. We find out this is actinium by looking at the periodic table. It's number 89. Here's another example of a carbon-14 nucleus undergoing beta decay, spits out an electron and becomes a nitrogen. So carbon can transform into nitrogen. Let's write a nuclear equation for the beta decay of actinium-228. So we start out with the element symbol, Ac228, and then we need the atomic number. So we look on the periodic table, it's 89. And we put the arrow. Beta decay means it's emitting a beta particle. A beta particle is an electron. Whoops. So the symbol for that is right there. That's something you have to memorize. That's a beta particle. We get those in place, and then we just do some simple math to figure out what the atomic number and mass number are for the daughter here. The mass number is easy because it doesn't change. And the atomic number actually goes up 1. So it goes from 89 to 90. 90 plus -1 equals 89. So we find element number 90 on the periodic table. It's thorium, TH. Any questions? So alpha particles are semi-trucks. Beta particles are four-wheel sedans. So they're less massive, right? They have lower ionizing power. You smash a four-door sedan into a brick wall, it's going to do some damage, but not nearly like the semi-truck, right? But then you think about the penetrating power. A four-door sedan will do much better in a traffic jam. So it will be able to penetrate better, but it does less damage. So beta decay can be stopped by a sheet of metal or a thick piece of wood, but it goes straight through paper or a t-shirt. It's more dangerous outside the body because it can get through your clothing and your skin. But it does less damage if it's swallowed or inhaled. Yes?
The example we just did right now, the top number for these beta decay, it always remains the same?
Yeah, because the beta particle has a mass number of 0, so it never changes. The third type of radiation is gamma radiation. And this is in the form of electromagnetic radiation. It's not particles in the same way that alpha and beta decay emit particles. Gamma rays are high energy photons, and we talked about gamma rays when we talked about electromagnetic radiation and electron transitions. The gamma ray has no charge and no mass, and so the mass number and the atomic number of the element don't change. So the symbol is the Greek letter gamma and 2 zeros here. Gamma rays usually are emitted with other radiation. So there'll be something will give off a beta particle and gamma radiation. What kind of a particle is this? That's an alpha particle. So here is uranium-238 undergoing alpha decay. It also gives off gamma rays. There's no way that you would be expected to know which ones give off gamma rays and which ones don't. If it says gamma radiation, then you write this. If it doesn't, don't. What are gamma rays like? They're like motorbikes, motorcycles. So low ionizing power, smash the motorcycle into the brick wall, not going to do much. But high penetrating power. Motorcycles can get through traffic jams, right? You think about a traffic jam on the freeway, and they can drive between all of the stopped cars. They get through really well. So gamma rays can go through lots of stuff. It takes several inches of lead to stop gamma rays, or very thick slabs of concrete. So pretty hard to stop those. The fourth one is positron emission. So what is positron? What is a positron? It's like an anti-electron. It's the antiparticle of the electron. If you get a positron and an electron and you put them together, they annihilate each other. They release a lot of energy in the form of gamma rays, but there's no matter left. In nuclear reactions, matter can be turned into energy, and energy can be turned into matter. But it's not simple. So in positron emission, a proton gets converted into a neutron and emits a positron. So this is kind of the opposite of the beta decay, where we had a neutron decaying into a proton and an electron. So we have one proton, and that's decaying into a neutron and a positron. The positron has the same symbol as the electron, with the exception of the charge. The charge is different. It's a +1. So when an atom emits a positron, the atomic number increases by 1. I'm sorry, decreases by 1. So here if we've got phosphorus 30 undergoing positron emission, it's going to emit a positron. The mass number stays the same, but the atomic number goes down. So it becomes silicon. Here's an example of a carbon-10 nucleus undergoing positron decay. And so that becomes a boron-10 nucleus, and this positron is emitted. The positrons are similar to beta particles in terms of ionizing and penetrating power, because they're the same size. Their charges are different. Yeah?
So basically on these, what we're going to end up would be like the neighbor atom?
Yeah, it's usually a neighboring atom, but it depends on how many particles it releases. It can release... Yeah, for positron and beta decay, it's going to be 1 different, but for the alpha decay, it's going to be 2 different. So we'll skip 1. So this is a table from your book that just sort of summarizes the different types, alpha, beta, gamma, and positron, lists the order of ionizing power, penetrating power, gives an example. So what do you need to know? you need to know the symbols for the particles, alpha, beta, positron. You should know the symbol for gamma. You should know their ranking in terms of ionizing and penetrating power, and you should be able to write a nuclear equation if given, like the ones we've done, where if they say radium-228 undergoes beta decay, you should be able to write the equation. Write a nuclear equation for the positron emission of sodium-22. Yeah, question?
In positron emission, if a proton turns into a neutron, how come the mass number doesn't change? I don't really.
Because you lost a proton. The proton became a neutron, and both of those are included in the mass number. So if you have one less proton and one more neutron, the mass number is the same.
Oh, because it also emits the proton from the electron. Okay, I got it.
So write a nuclear equation for the positron emission of sodium-22. Well, sodium, that's Na. 22, that's the mass number, and we get the atomic number from the periodic table, it's 11. So that's going to emit a positron. Positron, you can think of that as a positive electron. So no mass, but a +1 atomic number there. So to predict what goes in here, we're just making sure that the superscripts on one side equal the total of the superscripts on the other side. So here, that's not changing, it's still 22. Here we've got 11 on this side, and we need to know what plus 1 equals 11. Well, that must be 10, right? So this is neon. If you memorize the symbols for the different particles, writing these equations should not be difficult.